Swayam Prabha. Digital India. Educated India.
Welcome everybody. We are going to talk about hydroboration. What does that mean? It just means the alkyne is going to take a sip of water. It's going to get hydrated. So right now your alkyne's got a triple bond. We're going to add H2O across that triple bond. But the mechanism is not really very straightforward. It's got multiple steps. Now if you take a terminal alkyne, it is going to be regioselective and stereospecific. If you take an internal alkyne, it will be non-regioselective, but it's still going to be stereospecific. At least initial addition for both of these would be stereospecific. We're going to use hydroboration BH with two R groups here. For alkenes, we did BH3. Here, in order to make the regioselectivity even more pronounced, we put big bulky groups. So what are the R groups here? The R groups can be 9 bbn, so it's got like two horns, and they are going to then avoid bumping into these big groups. So that's where the regioselectivity comes from. Or it could be this, where you have a benzene group here, and that's going to try to stay away from the steric here and lie away from that towards the hydrogen. Now in this particular example, they got 70% of this when they used cyclohexyl groups here for R groups. For this particular example, this R group is going to be cyclohexane. Okay, and then it's going to be in a chair form. All right, let's look at it. So you have here a alkyne, and let's look at the mechanism here. And the alkyne is going to be octine 8, and there's a hydrogen. So it's really not at all symmetric. You got this huge R group and a teeny hydrogen on one side. So that really allows for some regioselectivity through steric. We could do electronic too, we could do strain, but in this case it's mostly steric. So if you bring this BH group here, where do you think it's going to sit? Is it going to sit so that the B is here and the H is here and your R groups are here? Or is it going to sit so that the hydrogen is here and the BR groups are here? What do you think? Steric. That's right. So if you have big R groups here, you want to go sit on the side of the sofa where you don't have all these pokey things, right? You don't want to go in here, sit on this big couch here and go ouch, ouch, and get poked by all of these hydrogens and carbons. So this has got a lot of steric. So this ain't going to happen mostly. This is the preferred pathway. So this is too much steric, and so we have regioselectivity. Because of that, the hydrogen is going to land on the carbon that's got fewer hydrogens. Now you know that's going to violate somebody's law, and who do you think that is? Markovnikov. This hydrogen going to the carbon with more hydrogens would be Markovnikov, but that's not preferred because of the steric, so it's going to do anti-Markovnikov, and that's where the regioselectivity arises. Anti-Markovnikov addition. If you put the arrows, boron, you can see has only 3 bonds, which means it doesn't have an octet. It's greedy for those electrons. It pulls that up, and the hydrogen then lands over here. And so now, if we go on our way here, we would have BH adding so that the hydrogen is over here and the boron is over here. So the boron hydrogen breaks, hydrogen makes a bond to this carbon, boron makes a bond to this carbon, and you have a transition state. Again, these are examples of your R2BH. In this case, we are using this particular reagent where R is cyclohexyl. Now the next step then is for all these bonds to gel. It doesn't even take a microsecond. For that, you are going to get addition all on the same side, which is why if you have a terminal, it's also stereospecific and regiospecific. So you have a hydrogen on one side and a boron, and just for good measure, I'm going to write those R groups out just for this one. So this is going to be an intermediate, and you can work this up just the way you did your alkene hydroboration. That is adding sodium hydroxide and H2O2. So when you add sodium hydroxide and H2O2, your sodium hydroxide is very, very basic, and it's going to pick up a hydrogen from here and give you a peroxy anion. That peroxy anion is very reactive, it's really unhappy, attacks the boron. Boron can go between 4 bonds and 3 bonds. When it has 4 bonds, it's got an octet, but at the same time it's a minus. So it gets rid of that extra group and comes back to this where the formal charge is 0, and that's happy. However, there's no octet. So the boron has 2 unhappy states. One is 0 formal charge and no octet, and the other one is -1 or charged, but it has an octet. So, well, it goes between these unhappy states, not deciding which one's better. All right, I know a lot of people go through that, and boron's not an exception. So it's just going through these 2 different oxidation states. So here you have a boron, and I'm going back to writing these R groups as R. As you can see, I don't have too much space. And we added the oxygen, and now it's a minus, and we want to get rid of that minus. And so what happens is the R group, keeping the configuration intact, it doesn't rotate and do silly things like that. It just keeps it just the way it is and moves over. And that means there's too many for that oxygen, and hydroxyl would leave, and this is in sodium hydroxide, so you're okay with that. This long tail, and your hydrogen now is going to have that boron on the oxygen. So now it's a borate ester on this side. And this hydrogen's here for the ride. Well, you know what happened later on with sodium hydroxide? Sodium hydroxide then attacks the boron and releases this. So here's your sodium hydroxide coming over, and you have plenty of sodium hydroxide. It's going to attack the boron. Oxygens love boron. Borons love oxygen. And you can see that's the play that we have between oxygen and boron over here. So let's see, so your hydroxyl attacks, your oxygen then gets off because there's too many things there. And so now you're going to have a hydrogen on one side and an oxygen minus on the other side. So here's your oxygen anion. Now this is called an enolate, okay? Alkene, so enolate. So the enolate is not too happy as an enolate because there's repulsion between these lone pairs and these pi bonds. It's a lot happier if it comes back and becomes a keto group. And you would see whenever you have enolate or enols, it will go to the keto form without an exception because the keto form is a lot more stable. So here is your oxygen double bond as your keto form, and here is an anion. Well, the anion on a carbon isn't that great. Oxygen anions are fine, but not next to a double bond. So the enolate goes to the keto. It's still unhappy. So we have water there because we have peroxide, and sodium hydroxide comes in water. So we have aqueous in there. So the water is going to protonate that, and you are going to get a very nice aldehyde. So aldehydes are very valuable things. A lot of your what you may call your spices like cinnamon and almond and vanilla and all of these have got nice aldehydes. They smell good, they taste good, and so we love them. So this is one way to make a nice aldehyde. Okay, and when you used octine and this borane, you got 70%, which is pretty decent. Your side products can be from the other regiochemistry and so on. But this is your major product, aldehyde. What would happen if you had internal alkynes? If you had internal alkynes, would you get an aldehyde, you think? Well, look at this. This hydrogen here is really, really hard to take off, and it's going to be there the entire time. And because you started with the terminal, that's the hydrogen that ends up here, so you get an aldehyde. But if you take the internal, there's no hydrogen here. So therefore, you are not going to get an aldehyde. Let's see what you get. You do the same thing, and I'm not going to redraw the whole thing. And I'm just going to use 9-BBN this time. A lot of your textbooks probably have 9-BBN, which is, well, it's got 2 bonds here and a octane, cyclooctane. So this is 9-borob 331 bicyclononane. That's where the name comes from, 9-BBN. Well, the same thing's going to happen. It's going to sit over here, but does it have a preference now? Both sides are going to be pokey. So it's going to sit both sides. It really doesn't have too much of a choice here. So you would have 9-BBN sitting like this. And there is steric. Well, turn around, and you're still going to have steric. So that steric's not going to go away just because you turn around, unlike here. Okay, so you're going to get steric either way. You're going to get poked by these. You're going to get poked by these ethyl hydrogens and carbons here, no matter what. So there's steric here, and there's steric here. So you got a rock in a hard place. There's really no ideal situation here. So both times you're going to get the same reaction, which is boron's going to pull up that alkyne pi bond, and it's going to drop the hydrogen here. Same here. Boron's going to pull up that alkyne hydrogen, and then it's going to land that hydrogen over there. So you're going to get after oxidation, and I'm not going to go over the entire mechanism. It's almost identical to that, except instead of 2 cyclohexyl groups, you're going to have these what do you call longhorns. All right. If you go to Texas, you got those big longhorns. They're really pokey things, and they're going to hit these no matter what. So you're going to get these longhorns giving you then this group, which gets oxidized through enolate, and you're going to get this. And your hydrogen is here. So you get 1 hydrogen from the boron, and you get another hydrogen from the water. So now you're going to get 2 hydrogens. So you will get this, which is why I said when you do hydroboration, you're just adding H2O. That's for this. And if you do this, you're going to get this boron adding here and giving you a ketone. And the hydrogen that came with the BH would be on the other carbon, and then it gets protonated with the enolate on the alpha position. So they're both going to be identical. If you turn this around, you're going to get this. If you turn this around, you're going to get this. So if you start with a symmetric alkyne, this is symmetric. You can cut this in 2 equal halves. You are going to end up with only one type of ketone. So this is really nice if you have symmetric alkynes. If you have asymmetric alkynes, let's say you have over here a methyl group or isopropyl group or whatever, and you have a propyl group, now, well, you may have some kind of selectivity, but not a whole lot. It's not like having a almost invisible hydrogen on one side. You do have a carbon with hydrogens and a CH2 with alpha group. So you don't really have a very good selectivity. And let's say you put some R2B, let's say you do the same 9BBN and then follow it up with oxidation. You're going to get 2 different ketones this time. You're going to get this 9BBN sitting on one side and the other side. So you'll get your carbonyl wherever your boron was sitting. You see, because your oxygen is inserting in here and that's becoming your carbonyl. And the next carbon, adjacent carbon, would have the hydrogen. So if you took that, if you had this boron sitting like this, you would get the carbonyl here. And then you get 1, 2, 3 over there. And if you had the boron sitting over here, you're going to put the carbonyl on that carbon. You see? So it really depends which direction this boron is going to attack that pi bond. And then you're going to get 1, 2. So the carbon chain here is going to be the same throughout. It's just the alkyne part, it's going to be a carbonyl. That's it. You didn't lose anybody along the way. So you have a 2 hexyne, and here you're going to get 2 different ketones because it's asymmetric. That's going to give you 2 types of alkynes. Here, you can't say that this is a Markovnikov addition because the hydrogen is going to a carbon that has no hydrogen. So there's really no Markovnikov or anti-Markovnikov. You could say it's non-Markovnikov here. So 9BB in addition to these alkynes that are internal are really non-Markovnikov. All right, so we have one more thing here, and let's look at that. One more example here. The main reason I'm doing this example is because Midland was my advisor, my PhD advisor, and I got to do this for him. This is called Midland reduction. It's named after him, Mark Midland. Well, alpine borane is something that's readily available, and what he did was he mixed alpine borane with 9BBN, and he got a reagent that can do enantioselective reductions. Now, enantioselective reductions are really big in industry because we want to get a particular enantiomer. Let's say R instead of S, or S instead of R. So that's really, really a huge deal. And let's see how this happens. How does enantioselective work? How do you just get one of the enantiomers and not the other, even though they are exact mirror images? Once you make them, it's almost impossible to separate them. So it's better to just make them just enantioselective. That's only make one of them, not both and separate. Just make one of the enantiomers. That's probably medicinally active. So here, the first thing that would happen is just the same reaction as before. And in this case, your alkene goes over here, and the hydrogen would go over here, and it will go on top because the methyl group is blocking it. So therefore, you would get a 9BB alpine borane, where you have the hydrogen up and a methyl group down. And then over here, your 9BBN is going to be up. And here's your longhorn. Now, this is the reagent. This is not the product. If you take this and put this with a propagyl ketone, if you put this with this reagent, it's going to selectively reduce the carbonyl because those are a lot more reactive. And the reason it's going to be enantioselective is because of the steric. Let's look at it. So if you draw these out here, if you draw the alpine borane, and your hydrogen is going to come out, and here's your methyl, and I'm going to draw it out because that plays a huge role in this. And here's your hydrogen, and here's your boron, and that's the moose head, or the longhorn over there. So that's going to cause a lot of steric here. This methyl is going to cause a lot of steric here. This molecule has to sneak in here, and it will sneak in such a way that this alkyne group here is closer to the methyl, because the methyl here has steric, and the alkyne is just like a tubular thing, so there's really no steric as such for that. So then we will draw your carbonyl out like this and put your triple bond toward the methyl. That's why you get this particular product. Now you're going to have your hydrogen go over here, and your carbonyl is going to go over here and catch that boron, and your pi bond is going to form. And so you're going to regenerate your alpine, and you are going to then have a reduction here, and after your oxidation here, you're going to get exactly this enantiomer. So steric plays a huge role in this. Because of the steric bias, this molecule prefers to have the alkyne group closer to the more sterically hindered methyl. And so you only get attacked on one side from below. And so that's your hydrogen over there. Just a little note, all borohydride reductions are stereospecific. The boron and the hydrogen can only add on the same side. So they're always going to be syn additions. All of the additions are syn. Whether it's internal or terminal, they're all going to be syn, because just the nature of the BH, you cannot go roll around and add on opposite sides. It's always going to be adding on the same side, syn. So stereospecific. But if you have a terminal alkyne, because of the steric bias here, you are going to get a huge amount of regioselectivity, where you add the boron on the less substituted carbon. So you would get an aldehyde if you start with a terminal alkyne, and you would get ketones if you started with internal alkynes. Now in internal alkynes, if you have a symmetric alkyne, then you only have possibilities for putting that carbonyl on either end of that alkyne. So you are going to get only one product because they would both be the same. If it is asymmetric, then if you put carbonyls here or here, you're going to get two different alkynes. It's still going to be syn addition, however, there's no regioselectivity. All right, so that's just to tell you there are lots and lots of applications to this. And one of the very important applications is the Midland reduction. All right, guys, I will see you soon with more reactions. Talk to you soon. Bye.